Okay, so for question 4, we're going to be doing some proofs for geometric random variable y with a probability of success p. Let's have a look at A. So we want to show that the probability that y is greater than a positive integer y is given by 1 minus p to the power of y. Great. So let's start with the left-hand side for now. Let's look at the probability that y is greater than y. So we can express this as, we can write this as 1 minus the probability that the random variable is less than or equal to y. Alright? And so then we can express that probability of less than in terms of the sum of the PEMF. So we have 1 minus the sum from I equals 1 up to y of 1 minus p to the I minus 1 times p. Right, so that means that we've had I minus 1 failures, and then on the yth attempt, we had a success. So on the ith attempt we had a success, and we're going to do that for all values of I up to lowercase y. Right, so it's just the definition of the CDF. Right, and then what we're going to do is we're going to write this as 1 minus p, the sum from I equals 1 up to y of 1 minus p to the I minus 1, right, because that p term has no dependence on y. And then what we're going to do next is we're going to try and deal with this minus 1 term, right, because we don't want that. So we're going to look at the indexing, right? So in this case here, I goes from 1 to y, but I minus 1 goes from 1 minus 1, which is 0, up to y minus 1. So we can write that instead as I goes from 0 to y minus 1 of 1 minus p to the I, right? And you can check that by putting in I equals 0, I equals I equals y minus 1 in this term, and compare it to the same thing in that term, and it should be the same. But the question then becomes, what is this? Right? What does that equal to? Well, we're going to do a little bit of an aside now, and we go through what that is. Okay, so this is aside. Let's, instead of dealing with 1 minus p, which is quite ugly, instead I'm going to write that in a slightly different way. So let's consider the sum from I equals 0, that's the same, up to n of x to the I. Right? So in this case, n is y minus 1, x is 1 minus p. Great. Now, given, okay, let's just write out the definition of that. So that would be, well, we know it to be 1, so when I equals 0, that is x to the power of 0, which is 1, plus when I equals 1, it's x to the power of 1, plus x squared, plus all the way up to x to the n. Okay? Now, why we do the next step is just because we need to show this is true. So what we get is we get x, if we multiply both sides by x, right, what we get is we get x plus x squared plus x cubed plus x to the n plus 1. Right, so what we've done is we've simply multiplied both sides by x, and now what we're going to do is we're going to subtract these two sums, right? So we're going to take this, and we're going to subtract from it this. And if we do that, what we get is we get x sum from I equals 0 up to n of x to the I minus the sum from I equals 0 up to n of x to the I, right? And what happens here is when we subtract them, you'll notice that this and this cancel, this and this cancel, this and this would cancel, and then the x to the n cancels with the x to the n here, right? And all that's left is the x to the n plus 1 term and the 1 term. So we have, and so we're subtracting this, this one minus this one, so we have x to the n plus 1 minus 1. Right? Now, that is, well, true and helpful. And so now we can solve for what that sum equals to on the left-hand side, right? So if we factorize out x minus 1 times the sum from I equals 1 up to n next to the I, that equals x to the n plus 1 minus 1 over... went one step ahead of himself. So that's what it's equal to, right? And now we can divide both sides by the x minus 1 term, and we know that I equals 1 up to n, x to the I equals x to the n plus 1 minus 1 over x minus 1. Right. So that's a true, that is well, a true statement. And what we can do now is we can connect that back to our p's and y's we had earlier, right? So if we finish the aside, right, go back to black, we know that this thing, right, is equal to 1 minus p times. Now, once again, n was our y minus 1. So everywhere there's an n, we can put in a y minus 1. So we have x to the y minus 1 plus 1, so that's n plus 1 minus 1 over x to the, x minus 1, right? However, once again, x is no longer x is 1 minus p. So what I should do is change that x and that x to be 1 minus p and 1 minus p. Great, so now we've used that information and we've used our little aside, and we can now just simplify it and hopefully get the answer we want. So you'll note that on the denominator we have 1 minus p minus 1, so the 1 and the minus 1 will cancel, right? So we'll have 1 minus p lots of, one other thing is that the minus 1 and the plus 1 cancel, so it's 1 minus p to the y minus 1 over negative p. Alright, now we're going to simplify it. We've got to be really careful with our negative signs. I made a mistake earlier when I was trying to solve this myself. So first of all, these p's can cancel, so we get 1 minus p to the y minus 1 over negative 1. Now, this negative and this negative can cancel, and so we have 1 plus 1 minus p to the y minus 1. And so now this one and this one cancel, and we're left with 1 minus p to the y. Alright, and hopefully that is the finished proof. So now we can move on to looking at part B. So part B wants us to show that for positive integers x and y, that this conditional probability is equal to the inverse CDF, which is hence 1 minus p to the x, which is what we just showed is true. Alright, so let's have a look at doing that. Alright, so we have B. So we want to show that probability that y is greater than little y plus x, given y has already exceeded y, right, is equal to the probability that y is greater than x. Okay, so let's start with this first term. So we have the probability y is greater than y plus x, given y is greater than y. Right, now that is a conditional probability because we have our given. So we can use the definition of conditional probability and write this in a different form. So we have the probability. Now there are two events that we're going to be taking the intersection of, so I'm going to use my curly brace. We have y greater than y plus x, right? And y greater than y. And then we're going to divide that by the probability that y is greater than y. Okay, so this is the definition of conditional probability, right? Because if we go up to here in blue, we have the, in terms of the notation, we have probability of A given B is the probability of A and B divided by the probability of B, right? And we've just written that where A is the y greater than y plus x and B is y greater than y, simply. Alright, so there's our little aside. Okay. So, what does the numerator of this right-hand side mean? Well, the numerator is asking for the probability that y is bigger than y plus x and y is bigger than y. So in this, there is redundant information, right? Because the probability of them both happening is independent of the fact that it has already passed y, right? Because x is a positive integer, y is a positive integer, so we know that y plus x must be greater than y, because positive doesn't include 0 in this case, and hence this term here has no effect on our probability if this term is also in the intersection, right? So what it actually becomes is that this line here, we can just drop that second term, right? We can just drop this one because it has no bearing on our probability. So it's equal to the probability that y is greater than y plus x over the probability that y is greater than y. Okay? So, now we've got this, we can use the definition of our inverse CDF. So, in part A, we showed that, I'll write my little aside, we showed that the probability y is greater than y is given by 1 minus p to the y. That's our little aside. So this is equal to, so in this case here, our y is now y plus x. So this ratio, the numerator, becomes 1 minus p to the y plus x divided by, now the denominator is the same thing as our previous question, so it's 1 minus p to the y. Now, hopefully you're comfortable with your index laws, and what you get is 1 minus p to the x, because the two y's cancel. And that is equal to the probability that y is greater than x. Great, so we've shown this now, and we can move to the next question, which, I've zoomed in crazy. Part C, which says, explain this memoryless observation. So, memoryless is a property that the exponential distribution has, right? Which we're going to show, which we've just shown. So, part C, this is mostly talking, not a lot of writing, but what we've observed, right, is that since each trial for a geometric distribution is independent, given nothing has happened by our yth trial, right here, then what's the probability that it'll happen by the y plus xth trial? In the sense that if we've already waited y time and nothing has happened, then waiting y plus x time means we've only waited x time beyond nothing already happening. Right? So what we end up with is that the probability that it takes more than y plus x, given it has already taken more than y, is simply equal to the probability that it will take more than x, right? Because this given statement over here is saying nothing's happened to y. So now if we wait y plus x, what that means is up to y, nothing's happened. Now we have to wait at least x amount of time to see something happen. And so we call this memoryless because in this line here, we've completely forgotten that y has happened. Right? We've said it has happened, nothing's happened until y, therefore we don't care about including y plus x in our probability, we only care that now we need to count x more independent trials until it happens. Okay? Okay, hopefully that is comfortable, and we can now move on to the next question. Alright, so the next one says, given that we have already tossed a fair coin 10 times and obtained 0 heads, what is the probability that we must toss the fair coin at least 2 more times to get the first head? Okay, so that's a bit of a mouthful, but let me just scroll past all of this. Okay, so D. So, okay, first of all, we have a fair coin, so the probability P is going to be a half, right? And so what we're saying is, given 10 trials has already happened, what's the probability that we see a success, or in this case, seeing a head, in at least the next 2 more times? So remember, at least means up to and including. So really what we want to find is the probability that y is greater than or equal to 12 given y has already exceeded 10. So this is saying, what is the probability that, given we've seen 10 tails, we don't see a head until the 12th or more toss, right? So that means that the 11th is also a tail, the 12th could be a head, the 13th could be a head, the 14th could be a head, and so on, up to infinity, right? So this here, given our, going in context of our previous question about memoryless, what we have is we have little y is equal to 10, little x is equal to 2, right? So using the memoryless property we've just discussed, this probability is equal to the probability that y is greater than 2. Oh, sorry, greater than or equal to 2. Right? Because of the greater than or equal to sign here. Now, we know that y, so up here we have that y is geometrically distributed with probability half, right? And so we can use that fact and the fact that we can write this as y greater than 1, right? Because exceeding 1 is the same as being 2 or more. And we can use what we calculated in the first part. And so this is equal to 1 minus our probability p, 1 minus our probability p, which is 1 on 2, raised to the power of x, or in this case 1. And what we end up with is a half. Okay, so that's an application of our memoryless property. Now I'm going to go through one more proof, which is part E, I think. Yeah. So we're asked to show that the probability y is an even integer, so 0, 2, 4, 6, 8, etc., is equal to this beast. Oops. This thing here. So let's go ahead and do just that. So let me scroll down. All right. E. So, first of all, we want to find the probability y is even, right? Now this is the probability that it's 0 plus the probability that it's 2 plus it's 4, 6, etc. However, we don't have to worry about the probability that y is equal to 0 because well, you can't have your first success on the 0th trial. So this is just equal to 0, so we can ignore that. Okay, now we're going to use the definition of a geometric PMF. And so what we have is that the probability that y equals 2 is given by there is one failure and then one success, right? Now if I had written in, as I should have, y equals 4, right? That is going to be 3 failures, so 1 minus p to the 3, and then 1 success, right? And then if we go to the next one, which would be 6, we would have 1 minus p to the 5 failures and 1 success, and so on. But that is horrible to write out up to infinity, so we're going to write it as a sum. So we have the sum from I equals 0 to infinity, right, where we have to have 1 minus p to the something fails and then 1 success. All right? But we want every even integer minus 1. Or in this case, because we're starting at 0, plus 1. So what we'll have is we'll have 2i plus 1, right? Because when I equals 0, this becomes 1, which is what we have over here. This is I equal to 0. When I equals 1, what we have is we have 2 times I, which is 2, plus 1, which is 3. So this would be I equals 1. This would be I equals 2, and so on. Now, we don't want to have this horrible power in our index, so we can remove it by having the sum from I equals 0 up to infinity of 1 minus p to the 2i, right? And then p, 1 minus p. Now, since the p and the 1 minus p have no dependence on I, we can pull them out in front of the sum. And so we get p, 1 minus p, times the sum from I equals 0, to infinity of 1 minus p to the 2i. Now, the next thing we can do is, using our index laws, we have, if you give me a minute, we have the to the power of 2i is to the power squared, is the thing squared to the power of i. So we can write that as 1 minus p squared to the power of I. Now, what does this whole thing mean? Well, let's have a quick aside, and then we'll come back to this problem like we did in the first proof, and we should be home free from there. So, let's look at the aside. Let's have a look at this. So this is a geometric series, right? So the first thing we have to check. So what we're going to use is the fact that the sum from I equals 0 to infinity of x to the I is equal to 1 over 1 minus x, provided that the absolute value of x is less than 1. Now that is because this is a geometric series, and proofs for that were done in first year maths. You can also do it by taking the result we derived in, I think it was part 1, and taking the limit for n goes to infinity, but we're not going to worry about that. So, in our case here, our x, in inverted comma, so we have x is 1 minus p squared. So, p is a probability, so it's between less than 1. So we have that p is less than 1, therefore 1 minus p must be less than 1, right? Therefore, 1 minus p squared is less than 1. So in this sense, so that means that we satisfy this condition. So we can now cancel our aside and go back to our problem. So we have p, 1 minus p, and we can substitute in this form for our sum. So we have 1 over 1 minus, and instead of x we have 1 minus p squared. 1 too many brackets. Which is great and all, but we have to simplify it so we can show that it's what Jono asked for. So what we can do is we can write this as p 1 minus p over, I'm going to expand that square, so we have 1 minus p squared plus 2p, right? But what we can do is these two ones cancel, and so we're left with p 1 minus p over 2p minus p squared, which is what we wanted.